Here it is today.
If you can't see the front board that's on the side, it's the same image.
Today what we're looking at, we're going to learn more about ratios. Why? So you can compare two different quantities. You'll know you got it at the end of the day if you can put the ratio in correct order and simplify. Your homework for today is page 12 and 15. Do not forget to finish your BOY assessment at the beginning of your assessment. That closes tonight. So if you don't finish it tonight, I don't know how I can reopen it. Our first task today is going to be equivalent ratios.
Right, so equivalent ratios. They're ratios, it's a different way to express the same value of a ratio by multiplying or dividing the two quantities of the ratio by the same number. That's the very important part right here, by the same number. So you have to, both sides, the first part and the second part, you have to multiply by the same number or else it's not equivalent. So looking here on the table, you'll see that our original ratio was 1 to 5. We simplified it. Can we divide it any further than that? No. So that's the lowest we can go. So what we're going to do to make an equivalent ratio, we're going to take the first term, multiply it by 2, we get 2. Take the second term, multiply it by 2, we get 10. So for now we have a ratio of 2 to 10. Again, here on the middle row, we took the first term, multiplied it by 3, we got 3. Took the second term, multiplied it by 3, we got 15 for a ratio of 3 to 15. And then we went one more step and multiplied both sides by 4, and we got 4 to 20. Now, if you take any of these equivalent ratios on the right-hand side and divide them by the number you multiplied them by, they're going to take you back to the original one of 1 to 5. See how that works? So they're all equivalent. They'll all go back to the original ratio. Pretty simple, correct? Yeah. That's an equivalent ratio. That's how easy it is. Any questions? All right.
Okay, so on this page what we've got is our equivalent ratio terms. I don't know how much of an impact it made for you guys, but I was sharing with you when I first became a teacher, one thing I learned was math is actually a lot more than just numbers, and that's where I was struggling as a teacher. It wasn't until I really thought of the math as a foreign language that it started to really make an impact for my students. So as part of that, anytime you learn a language, the first thing you have to do is understand the vocabulary, right? Because if I don't know what the words mean, being able to say them doesn't mean anything. So unfortunately, our text does not really do a good job of giving us the definitions. So we are going to actually add the definitions to our textbook. Okay? So what everyone to do right now is open up in your textbook to page 8. If you don't have your textbook, you're going to just need a blank piece of paper for today. You'll have to switch this over later on tonight. Okay? On page 8, you'll notice the page beside it is completely blank, right? So right here is where we are going to write our definitions. We're going to start making our own glossary of definitions for math. We have our first 3 for you up here today. I'm just going to say this up front, guys. For right now, you're taking notes. Write down everything that we have put here. It may not make sense to you. We're going to explain it. By the end of the lesson, all of these terms will make sense to you. So for right now, just write them down in your book. Do pay special attention to highlighted words. Those are ones that we've given to you before, so they're really important. So make sure you understand those as well. Okay? So we're going to give you about 5 minutes. It's only 3 terms. You should be able to write these down in 5 minutes. I'm going to pause the video for our home audience. So if you're at home, pause it so that you can write these down. Let's go over these terms. Excuse me. Really quickly. A ratio constant. Excuse me. The number used in a tape diagram to show how much each box equals in an expanded ratio. We'll show you that in a minute. It'll make more sense once you see it. Something still caught my throat, sorry. A tape diagram is a visual model of a ratio in simplest form. There we go. The boxes for the first term, the antecedent, go on top. The boxes for the second term, or the consequent, will go on the bottom. We'll show you how to make those in a minute. And then don't forget your divisibility rules. Remember, always use 2, 3, 5, and 7 with dividing ratios to find it in the simplest form. We're going to hit both of these a lot more as we go through today's lesson. They're going to make a lot more sense to you, but now you know exactly what those things are when you look back.
Okay, tape diagram in simplest form. Okay, reducing the ratio to simplest form makes the tape diagram easier to work with. So, right here we're comparing apples to oranges. As you can see, we have a ratio of 4 to 12. 4 being the apples, 12 being the oranges. And apples are represented by A, oranges by O. So, if we were to draw a tape diagram representing this ratio, you see we have 4 blocks on the top, and we're labeling them A for apples, and then we have 12 on the bottom, labeled it O for oranges. Now, if we were to work with that, you see how large that is? That's pretty big, right? And when we have to write the ratio constant in there, in each one of those blocks, and then you have to add them up, or you have to multiply and divide them, whatever the case may be, that's a lot of numbers to work with, correct? So, what we can do, and what you always want to do, is reduce it down to simplest form. So, we take 4 to 12, and we reduce it down to 1 to 3. How did we do that? Jaden?
You divided it by 4.
Yes, exactly. We divided each side by 4. So we divided 4 by 4, we got 1. We divided 12 by 4, we got 3. And that took us down to simplest form. We can't divide it any further. And now look at what you got. You got 1 block on top for the apples and 3 on the bottom for the oranges. And now that's a little bit easier to work with, right? Yes. Question, or you just stretch it? Hey. Okay. All right. So, you always want to reduce your tape diagram to simplest form to make it easier to work with, okay? Because that's the simplest form is the best starting point. Any questions on how to do that? Yes, Jake.
So with everything, do we make it all everything into this one?
When in a tape diagram, if you can reduce it down, and you'll see why in a minute, okay? Yes. If you can't reduce it if your initial ratio is already in its simplest form and it's big, that's what you have to work with. You can't reduce it any further than what it is. Okay?
Remember your 4 key numbers to check for reductions. Because just because they're not even doesn't mean you can't reduce. They may both be divisible by 3 or 7.
Yeah. Like I said, you have to take a look at it, and if the ratio they give you is already in its simplest form, and you can't take it down any further, well, that's what you have to work with. Okay? And it could be a little bit bigger than 1 to 3, but you can't go any further than that. So that's what you have to start. That's your starting point. Any questions? Okay.
Okay, so here's a tape diagram example. So in the 6th grade math class, there are 3 boys, or B, to every 2 girls, for a ratio of 1 to 3. Or 3 to 2, sorry. I was focused on moving that stupid thing. I forgot which one we're on. So first we're going to draw the tape diagram, and then we're going to talk about the ratio constant. Okay? So the first row on the top represents B. Why? Because it's the first thing listed in my ratio. So it doesn't matter which number is bigger, guys. It's whichever is listed first goes on top. Everybody good on that? Okay. The bottom row has 2 boxes. Why? Because my second number is a 2. It's that simple. We do label it, because the whole idea behind the tape diagram is I should be able to look at my tape diagram and I can really quickly get a whole visualization of everything it's telling me. So the tape diagram is really nice because I can look at this and say, oh wow, 3 boys, 2 girls, bang, makes sense. One thing you'll see on this one, we put 1 in as ratio constant just to show you how to put that box in there. Normally, if your ratio constant is 1, you just leave it blank. So if you're looking at a blank tape diagram, the assumption is your ratio constant inside of there is 1. Okay? So that being said, a couple other things I wanted to point out. Here are the basic things we expect to see when you draw a tape diagram. Your boxes should all be the same size. They should all be touching. So make your boxes per row touch and then make your 2 rows touch. Label them. Let us know what it is that you're talking about in your diagram. And then the final step is go ahead and add up what each row is and put that number there once you figure out what your ratio constant is. So in this case, since my ratio constant was 1, My first line ends with 3. My second line ends with 2, meaning that I have a 3 to 2 ratio. Make sense? Okay, now let's see if this makes sense. This is talking about a 6th grade math class. Do you think there's really only 5 people in that 6th grade math class? No. I mean, look at our class. You guys, this is the biggest one we've got. Okay, so here's where that concept of ratio constant comes in. So we just took an average of our classes, and we said, on average, our ratio constant was actually 5. Okay, so if we now look at our tape diagram with our ratio constant put in, saying where did we actually reduce to get the simplest form? What number did we start with? This is kind of like looking at the equivalent ratios where we're saying, here's the bigger one we actually started with. Okay, so we put a 5 in. So if I have 3 boxes of 5, how many boys is that?
15.
There we go.
15.
15, makes sense, right? If I have 2 boxes of 5 for the girls, how many girls is that?
10.
10. Makes sense, doesn't it? So again, to finish off our tape diagram, now that I put in my ratio constant, I now finish it's the 15 boys and 10 girls, meaning I actually have 25 students in the class. That makes a lot more sense, doesn't it? Okay? So what the ratio constant does is really gives us the equivalent ratio that we started from our initial ratio. Okay? Take our initial ratio, put the ratio constant in, now we're back to our expanded ratio, our equivalent ratio, to understand what the information actually meant. Everybody good so far? Okay.
Okay, so if you go to your first practice problem, which it says exercise 2, it's on page 8.
It's on the bottom of page 8.
Right. So it says Shani has 7 inches of ribbon. Mel has 3 inches of ribbon. How would your tape diagram look for this ratio? So how many blocks will we put on the top? Yes.
3.
On the top?
Yeah.
7. That's right.
Why 7?
It is the first number.
Yes, it was the first number mentioned. So that would go on the top. Now make sure that when you draw those 7 boxes, you write an S in front of it to let you know that those are Shani's 7 boxes. Now, so that means that the bottom one gets 3 boxes, and that put an M there to represent Mel.
Okay, go ahead and do that in your modules.
Now this thing, can we divide this down any further?
No.
No, so it's in simplest form. It is in simplest form.
Guys, make sure your tape diagram.
So now that you have your tape diagram, you have the 7 boxes on top, 3 on the bottom. So what would be our ratio constant if we were looking to get a ratio of 21 to 9? Who can answer that question? Yes, Abigail.
3.
Okay, 3. How'd you get that?
Because 3 times 2 is 9. And I know that 9 divided by 2 is 3.
Okay, so what Abigail did is she took the second number, and the second number represents Mel, correct? So she took those 3 boxes, she divided them into 9, and that gave her an answer of 3, which is correct. Okay, so she said it was 3. You would put your ratio constant there. That will equal the 9. Then you would put the same numbers in the 7 boxes on top. And that will give you your other number. See how that works? So once you get your ratio constant, you put that ratio constant in all of the blocks, and then all you have to do is add them up, or you can multiply them depending on how you want to do it.
Guys, if he's writing something on the board, you put it in your modules. So everyone should have copied down what he did with the ratio constant of 3 and the 21 and 9.
right, practice problem 2. Mason and Laney ran laps to train for the long distance running team. The ratio of laps Mason ran, represented by M, to the number of laps Laney ran, represented by L, is 2 to 3. Now, they gave you your ratio, correct? All right, so now you know what your tape diagram is supposed to look like. Now, the second part of this is, if Mason ran 4 miles, how far did Laney run? Draw the tape diagram and then find the ratio. So the first thing we're going to do here is something that we call marking the text. So the first thing you want to do is look at the numbers. Where's your numbers? And you want to circle them. You got your 2, your 3, your 4. Now you want to look at math terms. And you want to put boxes around them. So they're asking you for the ratio, right? So put a box around that, right here. Now, this is very important. What you want to do is whatever the question they're asking you, you want to underline. Here's the first question. Find the ratio. So you want to underline that. Here's another question. How far did Laney run? Those are your questions, and they should be underlined. That right there will let you know how to understand this better. You can see what numbers are there, the math terms that they're using, and what they're asking you to do. Here's another tip on how to figure this out a little easier. If I did this, that should help you. The 2 blocks on top equal 4.
Okay. Okay, so we can use that information they gave us to now find our ratio constant. Go ahead. Which will then help us answer the rest of the question. Okay? So using the Mason ran 4 miles, I have 2 boxes for that. So what's my ratio constant? Yes. 2. Make sense, guys? 2 boxes. Have to get them equal to 4. That means my ratio constant is 2. Here is the beauty of the tape diagram and the ratio constant. Once I have found the ratio constant for 1 box, every box in my tape diagram gets the same ratio constant. That's what makes this easy. So now I've got 3 boxes of 2. So what's the L? Yes? 6. Okay? So we've done our first part. We've got the tape diagram. So this is now a complete tape diagram. When we ask for a tape diagram, this is what we expect. We expect your labels. We expect to see your ratio constant in every box. And we expect to see your totals. Okay? But that's only one part of the question, isn't it? Okay? We're also supposed to find the ratio. So what's the ratio? Yes? 4 to 6. Excellent. Now, where I went to college at West Point, they always trained us, double underline your answer. That way it's easier for you to find. Because you guys are going to be grading your own work, and you'll see, if all I have is all this mess in here, sometimes it's hard to find your own answers. So do something. I double underline. You can circle, box, do something to make your answer stick out to you. So you can see that you've answered all the questions. Because I don't know about your side, Mr. Vasquez, but on my side, I have a lot of people that ignored the other part of the question. That's why we underline it. And the other part was, how far did Laney run? So what'd you get, Charter? Did you get to that part? So how far did Laney run? Okay. Well, that's what I asked. You said yes. Mimi. Excellent. Thank you for including the units. Now, because we're looking at word problems are always answered in a full sentence. So I would write, Laney ran 6 miles. And you must include the units. If I just wrote Laney ran 6, that doesn't really tell me much, guys. So it's Laney ran 6 miles. Have we now fully answered our question? Okay, I want to point something else out about the Engaged New York models. These modules, most of the time what they're going to do is they're going to give you one data set, and then they're going to ask you a series of questions off of that same data set. So you'll notice in part B, and now it's going to change things a little bit, but it's still talking about this. So what ratio are we going to use for part B? Lily? No? What ratio did they give us in the original data? Abigail?
2 to 3.
2 to 3, because this is the ratio they gave us in our initial data. So even though part B is phrased a little differently, we are still setting up our tape diagram based on the information we started the problem with. Make sense? So what is our initial tape diagram going to look like for part B? Hint, hint, hint. The big difference is our ratio constant is going to change. So I'll let Mr. Vasquez take over part B here.
Right, the next practice problem. If Laney ran 930 meters, how far did Mason run? First, you're going to find the ratio, and then you're going to answer the question of how far did Mason run. So again, you're going to circle the number. You're going to put a square around, or put a box around the terms, and then you're going to underline your question and tasks right there. All right, so it should look something like that. Here's another hint right here. It tells you Laney ran 930 meters, correct? So you can just do this.
Now, I was choking while we covered the tape diagram piece, but one really important part about this, guys, is they've always got to give you a third piece of information, or you can't really do anything with this. Without that third piece of information, you just get a pretty picture, okay? But when I get this third piece of information, that now allows me to do things mathematically with my tape diagram, because I now have the information to be able to find my my ratio constant. So really, the whole focus today, guys, is figuring out how does the information they gave me let me find my ratio constant so that I can now find what those equivalent ratios are. Make sense? Okay.
Okay, so we know that Laney ran 930 meters. And what we did was we put the bottom 3 blocks equal 930. Who can tell me what the ratio constant is? Okay, over here. That JJ. 310. How'd you get that? Okay. So that's the way he did it. Yes, Lily. Okay. Mm-hmm. Okay. So we did it 2 different ways. They came out with the same number. The easiest way to look at this is you're going to take the 3 blocks on the bottom. You're going to divide them into 930. That right there will give you 310. So we already established that that's our ratio constant. So we have to put that in here. So 310 3 times equals 930, correct? It's the ratio constant, so if we put them in these blocks, what do we got to do to the top one? Same number. Thank you. Gives me what?
620.
620. Now, we got our two numbers. We have to find the ratio. So what's the ratio? Who can tell me what? Yes, Armstrong.
Ratio is 620.
Yes, 620 to 930. That's your ratio. Now, the last part of the problem is, how far did Mason run? Yes, hey. Okay, so we have to write it out. And that's how you've answered the entire problem. Any questions?
No.
Okay. All right, so we're going to go straight into the problems because they're essentially the same thing as what you just learned. Now this one is a little bit tricky, so you're going to really have to think about it, okay? So the problem says, the morning announcement said that 2 out of every 7 6th grade students in the school had an overdue library book. Jasmine said, that would mean 24 of us have overdue books. Grace argued, no way, that's too high. How could you determine who's right? All right, so we find out, what are they asking? So here's the numbers right here, 2 and 7. So you're going to circle those. We're going to put a...
Guys, this is page 13 in your modules.
We're going to put a box around that because out of means that's another way to express the ratio.
Pop, page 13.
Here's another number, 24. That's the number of overdue books. And then our question is, how can you determine who's right? So they told us 2 out of every 7. That's your ratio, 2 to 7, correct? So there's your tape diagram. The 2 blocks on top are going to represent the overdue library books. And then the T is the total number of students, which would be 7. So you're going to have 2 blocks on the top, 7 on the bottom. Now, Jasmine said that 24 of us have overdue books. So where would that number go if we did the equal sign? And which, yes, Abigail.
The total?
What 24, she says 20 of us have what? Overdue books. So it would go on the top. Okay? With that information right there, you should be able to find the ratio constant. Does everybody see that? Okay, so find your ratio constant, fill in the blocks, and then give us the ratio, and then see if you can determine who's right. Is it Jasmine or is it Grace?
Okay, guys. So this is kind of my love-hate relationship with Engage New York curriculum, the one we're doing. Believe it or not, they gave you a trick question. Okay? You really had to understand what the data told you to be able to figure this out. So mathematically, I'm actually very pleased. Mathematically, you guys nailed this. I don't think I saw anybody that had the wrong mathematical answer. Okay? Everybody I saw said, okay, it's 24 overdue books. I got 2 boxes. So what's my ratio constant? What goes in each box? Mathematics? 12. And remember, the beauty about the ratio constant is once I have found it for one box, I have found it for every box in my tape diagram. So as soon as I have it there, I can now fill in all of these boxes, which means that this one equaled 84. Everybody I saw had this. And most of you even went this far and wrote down the ratio. Awesome, great, that's what we want. But the problem is, and here's where the Engage New York, this is why we mark the text, because Engage New York really wants you to think deeper about the question. So their question was actually, how can I determine who is right? Is Jasmine right that there's 24 overdue books, or is Grace right that 24 is too high? What's our missing piece of information that we don't know to figure out who is right? I'm going to go with Dylan because he was the first one that told me the correct answer.
The number of students.
Good, because we don't know the total number of students, do we? So the missing piece of information is, oh, that's pretty cool. Mr. Vasquez, you see what I did? I just pulled my marker down and all your typing's there. So we don't know exactly how many total students there are in 6th grade. If there are 84 students in 6th grade, then the information that Jasmine gave us is absolutely correct. But if there are less than 84 students, Grace is correct. Because if it's less than 84, that means this number needs to be smaller, because my ratio constant is going to be smaller. Make sense? So our missing piece of information, and that's where they wanted you to be able to link this and understand, these aren't just numbers, they mean something. That 84 means that that Jasmine was saying there's 84 6th graders. But if that's not the case, then Grace is correct. But if there are 84 6th grade students, then Jasmine was correct. Once we know how many students there are, then we would be able to tell who is correct. Does that make sense to everybody? Okay? This is something you're going to see very regularly with Engage New York. They do these deeper thinking questions. So don't get frustrated by it, please. Understand, if you can at least do the math, you've gone a long way. But once you finally start getting to where you're able to make that linkage and understand exactly what the question and answer is, that's where we're going to get you this year. Okay? So now we're going to do the next one. On this one, actually I'll turn it back over to Mr. Vasquez for this one.
Okay, you're going to decide whether or not each of the following pairs of ratios are equivalent. If the ratios are not equivalent, we're going to find a ratio that is equivalent to the first one. If the ratios are equivalent, then find the ratio constant that was used to get both of them. All right? So right now we're going to start with 1A, 6 to 11, and 42 to 88. Are those equivalent? Oop. And what you can do is draw an arrow from the 6 to the 42 and an 11 to the 88. And go, what do I have to multiply to get 42? Well, 6 to get 42, and what do I know multiply 11 by to get 88? Okay, so we're going to put an 8 here. What do we need to get 6 to get 42? Who said that? Bryce, 7. What do you have to get an equivalent fraction or equivalent ratio? You have to multiply them both by the same number, correct? Remember that? We said you have to do the first number and the second number. You have to multiply them both sides by the same number. Are those multiplied by the same number? No. So they're not equivalent. See how easy that was? All right, so what you want to do here is you got to take 6 to 11 and you're going to make an equivalent fraction for that one. You can give me an equivalent fraction. Yes. Yes, you can do that because what he did was he took 8 and he multiplied both sides by 8. So 8 times 6, 48. 8 times 11 is 88. What's another one? Yep. What was that? 7. Not quite. How about over here? Anybody? What's another equivalent? Okay, well, Dylan took 6 to 11 and multiplied by 8. He got 48 to 88. All you got to do is take 7 and multiply both sides, which gives you what? Or you can do what Mr. Moore always says and just multiply both sides by 2, which gives you what? That's an equivalent fraction, right? Or equivalent ratio, I'm sorry. I keep getting mixed up there. Equivalent ratio, because all you did was you took 6 to 11 and multiplied both sides by 2. Yes?
Or you could divide 6 and 42 and then take it as a remainder.
Not quite. Not quite.
No, because if you get into more advanced math, I could technically multiply them both by 6.5, and I would still have an equivalent ratio.
So, does everybody see how that works? Let's do one more. Who can give me one more equivalent ratio? You're always answering. We gotta get somebody else. Armstrong. If you took 6 to 11, what's an equivalent ratio?
Breaking our equipment, Mr. Pascal?
Yeah, sorry. It could be 18 to 33 because he multiplied both sides by 3. See how easy that is? All you have to do is, whatever you multiply the first number by, you have to multiply the second number in the ratio. Okay, so pretty simple. We're going to have to stop it right there because we have to assign you your homework and let you know how to do it.
Okay, so on the homework, everybody turn real quickly to page 12. This will be the big one. Go underneath. Page 12. Okay. One of the big things that students miss on this one is they're not reading what they're supposed to do. Write 2 ratios that are equivalent. Write 2 ratios that are equivalent. So if you only do one, do you get full credit?
No.
Thank you. This one, ratio of width to the height. Width goes which way? Left or right? Height goes which way? Up, down. So, should my numbers be in the correct order? Yes. Does it matter? Yes. Okay, we starred this one. Each squared, we basically gave you a ratio constant, guys. So if I just put that ratio constant in, tell me what the actual dimensions would be. Okay? Here's the other big one. On number 4, you'll notice there are 5 pieces to this. You guys are used to multiple choice questions. This is not multiple choice. That means using this information, answer all 5 of those questions. So I need 5 separate answers. Okay, sorry, real quick, page 15. This one's pretty easy. Make sure you're using diagrams. Show me 3 tape diagrams why they're equivalent. Use your simplified form, and then show me the ratio constant for the other 2. Same thing here. This one is use a diagram and the description. That's what Mr. Vasquez just went over with you. Show me what you would multiply to get there. That's the definition. This one is pretty easy, but you must read the question. That's all we got for you today, guys. Go ahead and pack up.